Now we can get back to it. We're going on to the last part of this chapter. It's a very important theorem that we need. We use it in multiple disciplines. If you've had ME 301 thermodynamics, you've seen it there. In fluids, of course, here too. It's called the Reynolds transport theorem. We'll do a little background first. We're going to be talking about systems and control volumes. The first thing is the control volume, as it says here, is a fixed region in space. So it's a particular region in space. You could analyze your hot water heater at home, in your garage maybe, or in the house, as a control volume. You can analyze a boiler as a control volume. All these pieces of equipment are typically analyzed by a control volume approach. Surrounding the control volume is a surface, a boundary. That surface is called the control surface. And these two guys are abbreviated CV and CS, control volume and control surface. So we're going to look at now mass crossing a boundary, which is going to be maybe the control surface. So we'll start off and here's some flow passage. It's a flow passage bounded on both sides. And we'll identify by a dashed line a control volume. The control surface is the boundary. We could call this, for instance, point 1 and this point 2. And maybe flow enters at 1 and flow comes out at 2. And we can also draw that, look like this. Take that control line out now, draw it like this. Or it might look something like this. So this is our control volume. And we could have velocity coming out here. This would be V2. This would be V1. I'll do a side calculation over here just to, I'm going to use that calculation in this derivation over here. So let's look at this real quick so you get an idea what we're doing there. Let's say there's a pipe here and we have flow coming in and flow going out. And we'll just label that B. The pipe's cut at an angle. The angle that it makes with this is theta. We're going to call this area right here A. And we're going to call this inclined area A theta. Okay. A is the cross-section area of the pipe. So if you took a piece of PVC pipe, cut it at a 45-degree angle, and let water run through it. The water is going to come out just like this, but the area is at a diagonal like that. The flow rate for this Q would be equal to V times A. Cross-sectional area, velocity. We mentioned this back a ways. You know, we had Q equals V times A, M dot equal rho times Q equal rho VA. So we've talked about that earlier in class. So the volumetric flow rate Q equal the average velocity times the area. Okay, let's rewrite this thing a little bit. Write it in terms of A theta. Get rid of A, make it A theta. So A theta times the cosine of theta. Same thing. Same thing. I'm doing a little right triangle there. This guy right here looks something like this. Magnitude B, magnitude A times the cosine of theta. That looks like the dot product. Okay, so if we want to deal with the flow rate Q, it's the velocity vector dotted with the area vector. Just one thing so you know. This area vector always points outward from the control volume by convention. Always points outward from the control volume. Okay, we'll use that over that derivation. So if we want to find Q over here, it's equal to V dot A. Don't forget, the area vector always points outward from the control volume. At 2, the area vector points outward from the control volume. At 1, the area vector points outward from the control volume. Okay, that's how you set it up that way. Now, that's not theta, pardon me, that's Q. If you want m dot, I put another word over there, m dot equal rho times Q. Okay. I guess I better put down, let's see here. Those vectors point in the same direction. The angle between them is 0 degrees. They're coincident, collinear. Okay, the angle between them is 0. Cosine of 0 is +1. So this sign here, cosine theta equal cosine 0 equal +1. Over here, cosine theta equal, two vectors are pointing opposite. The angle, 180. -1. So the dot product has a sign. If the flow comes in, it's negative. If the flow goes out, it's positive. The area vector always points outward from the control volume. If you want to label this again, we'll be real precise now, control surface. All right, so m dot is that, and then Q net equal the sum over the control surface of V dot A and m dot net equal sum over the control surface rho V dot A. Now don't forget, V dot A is positive if stuff goes out. V dot A is negative if stuff comes in. So this is the net outflow. M dot net out. What does net mean? Subtract something. The word net means subtract something. The net balance in your checkbook. Yeah, subtract something. What came in minus what goes out. In this case, it's what goes out minus what comes in. So Q net out then, in that case, would mean the flow rate leaving minus the flow rate entering. the flow rate leaving minus the flow rate entering. Okay, so that's just some background that we'll need for that. Okay, so let's go on. If an extensive property leaves the control volume, the dot means with respect to time, the rate of change of B with respect to time, B dot. V can be different variables. One of the most common ones is energy. We're going to do that in about 2 days, energy. So maybe capital B means energy. Little b is big B divided by mass. Capital B is extensive. Little b is intensive. So let's just, for the sake of giving it some kind of name, let's say capital B is energy in SI joules. Little b is then joules per kilogram. Okay, so that's what we mean by that. And if you want to be real official, and if it's not a uniform flow across the inlet and outlet, if it's not uniform flow, okay, that's uniform flow. That's non-uniform flow. Non-uniform flow. You can use a summation. If the velocity profiles varied across the flow area, then you have to be more official and use the integral definition. Because then V is going to depend on A, dA. Okay, so two possible forms of it. One for uniform flow, one for non-uniform flow. We'll pretty much deal with uniform flow for a while. So it's going to be uniform flow that we're looking at. All right, let's draw our picture one more time. I'll change it a little bit. A flow passageway. I'll draw the solid line here now. What's inside the solid line? Solid line is system at time t equals 0. That's a system. The control volume. Control volume, a fixed region of space. A system, a collection of matter, a bunch of molecules, of fixed identity. So, if I had a pipe system like this, where the flow comes in here and the flow goes out up here somewhere, if I want to do a system, I'll say, okay, I'm going to take these particles and I'm going to spray paint them maybe, I don't know, green. So here is, there's a system at time t equals 0. This is water in a pipeline. Wait 15 seconds. It's up there now. Wait 30 seconds. It's down here now. Wait a minute and a half. It's up here now. Wait a minute and 3/4. Comes out of here. There it is. Identify every particle, got a number and a name. Particle A1, B2, C10. Everyone's tag, name. Fixed identity. We don't do that generally in engineering. If I'm analyzing my hot water heater in my garage, I'm not going to watch the water molecules come from the city water supply, go into that water heater, get heated, and end up going out the faucet in the kitchen. No. I'm going to draw a system boundary around that hot water heater, and I'm going to analyze what comes in, cold water, and what goes out, hot water. Now, over here, if I want to draw a control line, I might say, I'm going to look at this pipe fitting. It's called an elbow, a 90-degree elbow. I'm going to analyze that 90-degree elbow. That now becomes a control line. Okay, back to here again. That's like this. I'm going to follow those particles. But Reynolds transport theorem is a missing link type equation. Most of the laws in science, physics, and so on are written for a system. Okay? In engineering, though, we do a lot of control line studies. So this theorem allows us to take basic laws written for a system and convert them to one more useful to us, the engineers, which are in a control line form. Okay, so what I'm going to do now is I'm going to try and relate the control line to the system. All right. I'm going to call that same volume at time 0 my control volume. Okay, so here's my control volume. Okay, that is also going to be my control line. This is the control volume for any time. Remember what it said, control volume. Fixed in space, not moving in space, fixed. So that's the control volume. I choose to make a coincident at time 0. Okay, wait 30 seconds. Does the control volume move? No, I'll say it again. Fixed in space. Does the system move? Yeah, I just showed you. Now the system moves to a new location, down that way, because the velocity is here. Okay, now, where's it now? Okay, that was a solid line. Now it's going to be a dashed line. Dash line. System. At time t, I think I call that just dt, yeah, delta t. Okay, now we'll go way back over here. Next step for the system. dB dt in the system. The amount of B, how does the amount of B change with respect to time in the system? Don't forget, if you get confused, just say to yourself, energy. Okay, energy. If you watch a cubic inch of water come in from your cold water pipe and hot water heater, and you watch it go through the hot water heater, do you think it's going to change the energy? Oh yeah. Why? Because you're adding heat from the natural gas burner. Yeah, as it moves through the hot water heater, it's going to change its energy. Well, B is like energy. B can be various properties: energy, momentum, mass. So, this is the time rate of change of the amount of B in the system. Start off, basic definition, what is a derivative? Limit as delta t approaches 0 of the amount of B in there at time t plus delta t minus the amount of B in there at time t equals 0. T equal t. We won't call that 0. We won't use a 0, just call it time t. Divided by, what was the time change? Delta t. Equals okay, the amount of B in there at time t plus delta t. I'm going to call this region 1, this region 2, this region 3. At time t equals 0, there's the system, black line. The amount of B in region 1 plus the amount of B in region 2. Let's put that here. Let's do it this way. I'll put this down first and explain it. I'm going to keep this in the right order. The amount of B in region T was the amount of B1 plus B2. T plus dt, system at T plus dt, dash lines. 2 plus 3. 2 plus 3. Okay. Keep going, rearrange. dB, dt, system. You can see where the terms came from. Yeah, nothing new was added. It was just moving the terms around. This term is this term. This term is that term. This term is that term. This term is that term. Yeah, just rearranging the two. Okay, let's look at this term first. The amount of B in region 2. Okay, what's region 2? Region 2. That's right here, okay, in the middle here. In region 2 at time t plus dt at time t. Okay. All right, so this guy right here in the limit, dB, cV, dt. This guy right here, what went out minus what came in. What went out minus what came in. The amount of B that went out minus the amount of B that came in. Okay? So this term right here, okay. So we got, now where did this guy here come from? I just erased it, unfortunately. Maybe it's still up here. Yeah, okay, here it is right here. B rho B dot A is what came out minus what came in. So that's what that term is. Let's then combine these two into one equation. We'll put that up here, I think. Okay, dV system, dt. d dt. Okay, now we did this guy right here. This is the amount of B in the control volume, the change of it with respect to time. This is the amount of B in the control volume. So this is B in the control volume. Integrate over the control volume. Let's see what the integration is. What is, I'll just pretend it's SI. What is B? Okay, let's just say B is joules again, just to make something up. Energy in joules. So B is joules per kilogram. What is rho? Kilograms per cubic meter. What's the volume? Cubic meters. When you're done, what do you have? Joules. That's the amount of B in the control volume as a function of time. That's what the interval represents. If it's steady state, of course, goodbye, nothing compared with time, that term goes out for steady state. Okay, we're almost there. This one, time rate of change of B in the system. This one, time, rate of change of B in the control volume. This one, net outflow rate of B. Okay, This guy here, if you want to, if it's not uniform flow, okay, remember, not uniform flow, or if not uniform flow, then we have the integral of B, rho B dot N dA. This guy, unit vector in the n direction. Okay, I can't box it in, there's too much up there. That final equation right there, in symbolic terms and word terms, that is the transport theorem, Reynolds transport theorem. What does it relate? Well, it relates on the left-hand side, and there's the word, of course, changes in the system, as the basic laws of science are generally expressed in. We engineers want it expressed in control volume terms. So the right-hand side is the control volume terms. Control surface there, control volume here. If it's steady state, that term goes out. Okay. So that's what we're going to use for mass, momentum, and energy in Chapter 5. We'll let capital B be mass, first of all, then momentum, and finally energy, and develop 3 equations from that Reynolds transport theorem. Okay, so you have an example for homework. Let me see which one I assigned. Yeah, you have 68 and 69. I'm going to work problem 70. It's somewhat similar to 69. So let me, I don't need this. I need that over there maybe. Oh, we'll see. Okay, let's see what problem 470. Let me draw a picture first. Here's a picture given in the textbook. There's 2 plates pulled in opposite directions. And let's see here. The speed of the plates are 1 foot per second. So this plate is being pulled this way, velocity equal 1 foot per second. And the other one is being pulled to the left at 1 foot per second. Okay. Oil is between the 2 plates. I'll just put it here. Okay. Velocity is 10y times I. Y is measured from the middle. And the distances are, let's see, 0.1 feet. Oh, I'm sorry, 0.2 feet. That's sweet. Let's just make sure that's what it is. 470. No, it is one. It's 110. Yeah, 110. 110. Okay, now let's see what I have to find. Okay. Fixed control volume, A, B, C, D. 2/10, 2/10. Okay. Fixed control volume. Okay, let's see. A, B, C, D. Got it. That is showing, this coincides, CV coincides with system at t equals 0. So here's the system at time 0. Okay, the system at time and the control volume for any time. Control volume not moving. This is the fixed control volume. Okay. Okay, let's see now. That's still given. Keep reading. Indicate the system at time t equal 0.2 seconds. So system at time 0.2 seconds. It's going to be a solid blue line. The velocity, okay, let's draw the velocity. At the center, y equals 0, velocity equals 0. Okay. At the top, y equal 1/10, v equal 1. I've already put it there for you. At the bottom, y equal -1. Points left. Yeah, v is 1. Between the two, v is a function of y only, linear. Linear. So it looks something like this. There's the velocity field for the oil. After 2/10 of a second, did the oil molecule in the middle between the plates move? No, because the velocity is 0. Did the oil particle at the very top move? Yes. Which way? To the right. How much? It's going at 1 foot per second. For how long? 2/10 of a second. 1 times 2/10, it moved over 2/10 of a foot. By the way, I didn't put this on it, but it started out at 2/10 and 2/10 here. This was given. Okay, so that top oil molecule was right there at time 0. 2/10 of a second. It moved over. 2/10 times 1, 2/10 second times 1 foot per second. 2/10 of a foot. Where did it start out? 2/10 of a foot. Where did it end up? Another 2/10 out. This particle moved out here to there. Where did the middle particle move? It didn't move. How about the one down here? It went the other direction. This guy right here, where the big blue point is, he went to the left. How much? 1 foot per second times how long? 2/10 of a second. He went 2/10 that way. He's back here. Now, the guy up here, at point B on the plate, oil molecule, which way is he going? To the right. At what rate? 1 foot per second. For how long? 2/10 of a second. He moved 2/10 of a foot that way. He's up here. The guy in the middle, did he move? No. It's linear, of course. The guy at the bottom, at point A, the oil molecule on that plate, did he move? Yes, he did. What's his velocity? 1 foot per second. Which way? To the left. For how long? 2/10 of a second. 2/10 times 1. Okay, he's out here now. 2/10. He's right here. Now, the blue. In this chapter here, you better have multicolored pens and good sketching techniques because you're going to need it. This is not, and don't make these things postage stamp size. You'd be crazy when you get done. Make them big. So that's the answer. Where is the system after 2/10 of a second in the blue boundary? It got skewed like this. The last part says, identify the amount that was leaving and the amount that came in. Okay, this is 1. This is 1. This is 2. Now let's make that 3, maybe sensible. We'll make that 2. It's 4. Three left, 2 out, so 1 and 3 out. All those fluid molecules moved out of the control volume. What came into the control volume? These guys that were on the edge, they came in. These guys that were on the edge, they came in. 2 and 4 came in. So some fluid came in, some fluid went out, carrying the property capital B. So again, what did you start out with? The control volume and the system were coincident. Then what happened? You wait 2/10 of a second. Draw the new system boundaries. I did, the solid blue line. Third part, identify the amount of material that came in and went out of the control volume. 1 came out of the control volume. 3 came out of the control volume. 2 came into the control volume. 4 came into the control volume. Your problem homework is just about like that, but a different geometry. Identify the system after a certain time, show the stuff that came in and the stuff that left, and sketch it. And it's just trying to explain to you about the Reynolds transport theorem, what it means. Okay, now our last step today. Our last step is we're going to start with number 1. We're going to let B be a certain quantity. I told you there's three. It can be mass, momentum, and energy. We're going to do all three. Today we'll take the easy one, mass. Pretty easy for your hot water heater. If you got a gallon of cold water coming in from the city, guess what's going out to your dishwasher in the kitchen? A gallon. Why? It's steady state. What comes in equal what goes out. So yeah, you know, some things are pretty straightforward. So let's look at our mass then. We'll call this. Let's put it right here. Call this continuity equation or conservation mass. Let capital B equal the mass of the system. Then little b equal mass of the system divided by mass. So of course little b just becomes 1. Kilograms per kilogram is 1. Dimensions in other words. And the transport theorem says the following. Don't forget now, capital B is the mass. D mass dt of the system equal d dt. This is the control volume. Don't forget, little b is 1, so there was a little b in there, but little b was 1, plus integral over the control surface, rho v dot dA. Okay. On the board, we had, oh, still on? Yeah, okay, good. On the board, a system is a collection of matter of fixed identity. I showed you the pipe. If there is 1 pound of water at 1 minute and you tag them with some kind of spray paint or something, after another 2 minutes, did their mass change? No, because you're following the same particles. So the mass is not changing for what? A system. So this term here is 0. That's the system approach. It says conservation of mass. If we don't lose particles or gain particles, we have the same particles, then their mass didn't change of the system. Okay, so now this becomes ddt, integral control volume, rho dV. Don't forget V slash is volume, V no slash is velocity. I mean, there's some people aren't too good about that, and they don't make a little b very good with a big V. I saw them in the exam sometimes. There's a difference. Little b is the velocity is a component velocity vector. It's in the y direction. What's big V? It's a velocity. It might be the average velocity, we don't know. It's a velocity. But this guy is a specific velocity in the y direction. And the V slash is a volume. Okay, anyway, back to here. I'm going to assume uniform flow again to make things simple as we go through this. So our flow in whatever it is, in pipes or whatever it is assumed to be uniform. It doesn't change with the cross-section area. So get rid of the integral and make it the summation over the control surface of rho v dot A. Okay, now, if the flow is one-dimensional and steady state, Okay, then if that's the case, the steady state, this guy's 0. So this term here is 0, okay? Of rho v dot A. Don't forget, those two terms are 0. I'll put it down here. So if it's steady and uniform flow, one-dimensional, then we got this guy right here. Well, don't forget what that is. I had it before. It's in your notes. This guy here is a mass flow rate. Don't forget, if it leaves, it's positive. If it comes in, it's negative. So this is m dot in equal m dot out. If you want to do it officially, then it looks like this. Outflow is positive, so rho out, V out, A out, minus, if it comes in, it's negative sign. Rho in, V in, A in, equals 0. M dot out minus m dot in equals 0, which gives that guy right there. Okay. Next step, if it's incompressible, also, besides being 1D and steady, rho in equal rho out for steady flow. Okay, so here we go. Cancel out the rows, cancel out the rows. So B out, A out equal B in, A in. RQ out equal Q in. Okay, box them in here. Okay, those equations carry with them some assumptions, and they better be true or don't use them. Number 1, steady flow. Set it up here. Number 2, uniform flow, 1D flow. If those two are the assumption you can make, then m dot in equal m dot out. Of what? The control law. If the fluid is incompressible, or can be treated as incompressible, then the densities are the same, in and out. Then you can say the volumetric flow rate in equal the volumetric flow rate out. That's what I said. If 1 gallon of water goes into your hot water, your cold water, guess what happens? 1 gallon of hot water goes out the other end. Why? Because in your hot water heater, the flow is steady, 1D, and the fluid is incompressible. But if those aren't true, you have to go back to the basics like this. If it's not steady, you got to use the integral. If it's not uniform, pardon me, use the integral. If it's not steady, keep him in there. Okay. So that is the conservation of mass. Okay, I think it's a good stopping point. I don't want to do the example because I won't get finished with it in the time we have. So we'll stop for today and pick it up then on Monday.
What does m dot call that?
The mass flow rate. Remember we have rho AB up there? M dot rho AB. It's a mass. It's called the mass flow rate. And V, Q is called the volumetric flow rate.